Chapter 2. Applications of Integration. Introduction. Chapter 2 explores various applications of integration in physics. It covers topics such as calculating mass from density functions, determining work done by variable forces, finding hydrostatic force against submerged objects, and understanding exponential functions and logarithms. These applications provide practical examples of how integration can be used to solve real-world problems in physics. Learning objectives. By the end of this chapter, you should be able to 1. Determine the mass of one-dimensional and two-dimensional objects using density functions. 2. Calculate the work done by variable forces acting along a line. 3. Find the work done in pumping a liquid from one height to another. 4. Calculate the hydrostatic force against a submerged vertical plate. 5. Understand the properties and applications of exponential functions and logarithms. Key points. Integration can be used to calculate the mass of one-dimensional objects by integrating the linear density function over a given interval. The mass of a two-dimensional circular object can be determined by integrating the radial density function over the area of the object. Work done by a variable force acting along a line can be calculated by integrating the force function over the distance traveled. The work done in pumping a liquid from one height to another can be found by integrating the product of the force of gravity and the change in height. The hydrostatic force against a submerged vertical plate can be calculated by integrating the pressure function over the surface area of the plate. Exponential functions and logarithms can be defined and understood through integration. Real-world application. One real-world application of integration in physics is calculating the mass of an object with varying density. For example, in engineering, it is important to determine the mass of a bridge or a building structure to ensure its stability. By using integration to integrate the density function over the volume of the object, engineers can accurately calculate the mass and make informed decisions about the design and construction of the structure. Additionally, exponential functions and logarithms are used in various fields such as finance, biology, and computer science to model growth, decay, and other phenomena. Conclusion. Chapter 2 introduces various applications of integration in physics. By understanding and applying the concepts and techniques covered in this chapter, you will be able to solve a wide range of physical problems. Integration plays a crucial role in calculating mass, determining work done by variable forces, finding hydrostatic force, and understanding exponential functions and logarithms. These applications have practical implications in fields such as engineering, architecture, finance, and biology. By mastering the techniques and concepts covered in this chapter, you will be equipped with the tools to analyze and solve real-world physics problems. So, dive in, explore the physical applications of integration, and discover the power and versatility of this mathematical tool in the world of physics.